BJT amplifiers are only slightly different from MOSFETs, partially because MOSFETs are considered always transconductance amplifiers. So that means there is a voltage, and the voltage controls what the output is, the input voltage of VGS. With a BJT, we can actually look at it two different ways depending. Can look at it as a transconductance amplifier also, where we look at the base emitter voltage, which is pretty much analogous to the gate source voltage in a MOSFET. But since we also have the relationship between the input and the output, which is relating either using either beta or alpha, depending on what the configuration we have, we can also look at it as a current amplifier. And in fact, I think when I learned about BJT amplifiers, we didn't even cover MOSFET amplifiers because that was so long ago, we only looked at the current part. We actually didn't even look at the transconductance part, but now that we use MOSFETs more, the transconductance amplifier model looks almost exactly the same as what we did with MOSFETs. It's very, very similar. So we can look at the voltage transfer characteristics of a BJT. We did that with MOSFETs. It looks slightly different with a BJT. Note that the areas are marked differently. So with the MOSFET, we had the triode region, then the saturation region, then whatever was to the right of that. And now it's been a while and I don't remember. I think it's turned off there. But we have cutoff and then active mode, and active is where we're supposed to keep the BJT if we want to use it as an amplifier, and then we have saturation. And with a MOSFET, when we got out of the region where we amplified, it just kind of turned off. And in the case of a BJT, it actually stabilizes at a VCE value of about 0.2 and doesn't go lower than that. So that's kind of the limit. So you notice that the voltage transfer curve, rather than going down to zero, it never actually does as VBE gets bigger. It never actually goes to zero. VCE just stays at 0.2 volts. And you'll also notice that there is an equation that describes that curve, similar to the equation that described the curve with MOSFETs, although not exactly the same. We do pretty much the same thing when we're trying to figure out where the Q point should be. We have to put the operating point in the middle so that it's not going into saturation or cutoff. And what we try to do is get the value of VCE, the DC value of VCE, to be about halfway between VCC and 0.3, which basically usually if we take VCC and divide by 2, that's close enough, because we're never going to get it exactly. So if we had a VCC of 20, we would not generally be able to get a VCE of like halfway between 20 minus 0.3, but we would try to get it to be about 10 if we could, depending on the design. You try to get it to the half point, and sometimes you can, and most of the time it's a very general area. If I have a circuit and I'm designing it and VCC is a value and VCE comes out around half, then I'm fine with that. You're just trying to get kind of in the middle so that you have the maximum swing. So the Q point would go kind of halfway between VCC and 0.3, and you notice that the VBE line, we've got 0.5 marked on the left, and then you know VBE is really usually around 0.7, so there's not a great deal of variation for VBE, so we don't really worry about where that falls. It obviously has to fall in the saturation region, or in the active mode. Gosh, I'm still in MOSFETs, aren't I? Has to fall in the active region, but it's going to be around 0.7, and we just sort of assume that. In order to have linear operation, we have to keep the transistor in the active region. We have to keep the input signal small, and then we get the AC small signal parameters for the model from the DC Q point. That's just like the same thing we did with MOSFETs. We had to find the drain current, and we needed to figure out what GM was, and once we knew the transconductance, we just took that and put it in the model for whatever value that would be. So we can also look at the traces with the base curve, what do you call those? The base current curves, there we go. That is the more standard way of looking at curves for a BJT, and we want the active region again to be centrally located as far as the Q point goes. Okay, so we still want the Q point to be such that when it moves and the operating point moves up and down that line, it stays inside the active region. So putting it kind of in the middle gives us the maximum amount of swing we can get to the output, which is what we need so that it doesn't clip. So when we talk about amplifiers in general, we need to know what the transconductance value is. That is the parameter, well, there's one of two, but they're related. Transconductance or small signal AC resistance are going to be related to each other. But we want to split up the base emitter voltage into its DC and AC parts, just like we did with MOSFETs when we took the gate to source voltage. We split that into its DC and AC parts, which I'm sure you don't remember because that was like 3 whole weeks ago and like on a different test. So if I show it to you again, it won't matter because you'll think it looks familiar but probably not remember the context, which is the great thing about teaching. So if we look at the collector current has an equation that describes it. And we can actually go through and solve for just the AC part of the current. And you will notice that the AC part of the AC current has the DC as its sort of initial value and then the exponential after it. It's similar to every other exponential function you encounter in circuits. When you do charging and discharging capacitors, it ends up being an exponential. With inductors, it ends up being an exponential. In here, it ends up being an exponential. So this is a kind of a common equation. Since VBE is really small, and it has to be really small because remember the DC value of VBE is only 0.7, so there's not much wiggle room in that particular area, so we try to limit that significantly. And so VBE is usually a lot less than the thermal voltage. The thermal voltage is about 25 millivolts, and we try to keep VBE to 5 or 10 millivolts. And so we can approximate the exponential this way, where we just have IC, the DC value, times 1 plus VBE over VT. So we're getting to the point where we can figure out how to find the transconductance from this. So when we look at this equation and rearrange it just a little bit, we have IC, and it's kind of a hazy thing, but if you see a little letter for V or I and then a capital for the subscript, that means it's a combination of AC and DC. And I try to be consistent with that, and I try not to use that very often. I try to either use DC or AC, but sometimes you have to combine them. So this is basically saying that the AC-DC combination of the collector current is the DC current, which is IC, which is both capital letters, plus IC over VT VBE. That's the AC part. So we can actually take out the AC part, and that basically gives us the transconductance, because basically I over V is going to be the transconductance, so that's how you get it. And that's what I think I sent an email out last week saying this is how you find it, because the lab asked you to find it. So this is very, very similar to finding the transconductance for MOSFETs. Remember, with that was ID over VT, so it's very similar. We also have the same thing with BJTs as far as finding the slope of the actual curves. If we look at them, they're not actually horizontal. It's just like with MOSFETs. If you look at the VBE curves, they actually do kind of tilt up because there is a base emitter channel, not channel, but it's like the base width of the depletion region changes. So because it changes, there's a bit of an upswing in the values of VBE as you go up, and that's due to the fact that when you extrapolate everything back, you get this V sub A, which has a name for BJTs. It's actually called the early voltage after Mr. Early, who discovered it. I guess he was probably Dr. Early, not Mr. Early. But it was discovered with BJTs first, and then they discovered the same things with MOSFETs, so they didn't call it an early voltage with MOSFETs, they just called it V sub A. But it actually came from BJTs first. And the slope of the line in any given point, if you know what VBE is, the slope of that is just the transconductance, which is pretty much the same thing we got with the other things, MOSFETs. I think I either spent too much time outside or something, because I'm all got camping throat again. But I wasn't camping, but I was at the mountain on Saturday. Yeah, that always does it every time. Yes.
Do you think that was an early discovery?
It was early, I will say. In fact, I think they discovered it with tube transistors and not even like solid state transistors. I think so, yeah. So the things that we need to find when we do the DC analysis and the models that we use, that's all I'm going to sort of talk about today. First of all, we oftentimes look at the base resistance. So we look into the base, and VBE is kind of right at the base of the transistor. And the definition of this base resistance is just the AC value of VBE over IB. That's never how you find it. That's just the definition. So don't go looking for VBE and dividing by IB, because that's not going to give you the value. The values that you're going to use are generally going to be either the second or the third, and they are entirely equivalent. You can take beta over GM and get this R pi value, or you can take VT over IB, and it's all the same. You can see to the left how you get from one to the other. So basically, if you know transistor parameters, you can find the base resistance, or if you just know the DC quantities, you can find the base resistance. And this is one of the values that goes into the model. In fact, it was on Friday's participation assignment. It was listed as a parameter because it's used frequently. So if we have, say, a BJT amplifier with a constant collector current, and that's the DC value, and there's a range of beta values, we want to know what the range of the transconductance, the base current, and R pi would be, depending on the situation. So we can find the transconductance really easily, and that's not going to change because it already said that IC over VT is going to be, IC is going to be constant and not going to change. So the value of IC isn't going to change. The value that may change would be IB, and then R pi would also change because they depend on those other values. So we can find the range of base currents just by taking IC over the large value of beta, IC over the small value of beta. That gives us the range of base currents we could have. And then in the R pi values, we just take the thermal voltage and divide by IB, the two different values are the different values we found, and we find a range for R pi. So that can make a big difference depending on the application that you're using. So that's one type of resistance that you may encounter in models. The other one is the emitter resistance, which is little r, little e, and that's also seen by VE. So again, we have a definition of it. The definition is just VBE over IE. That's not how you ever find it. You never do it that way. You'd use the second two equations for the same reasons that you would find R pi that way. You either take alpha over GM or you take VT over IE, and those are absolutely identical. So what is the difference between these two resistances? That's kind of the big thing. They're actually the same thing on two different sides of the transistor. So if you look at the transistor and you look at the one on the left, R pi is looking into the base of the transistor. RE is looking into the emitter of the transistor. It's the same exact resistance, but it looks different because of the current going through it, if that makes sense. VBE is always the same. On the right-hand side, we're looking at the resistance, looking in with IE going through that emitter leg, and so it looks like a small resistance because IE is a large current and VBE is the same. On the left-hand side, R pi is looking into the base. The base current is really small. VBE is the same, but since the base current is small, R pi is bigger. And we relate the two, since we can relate IB and IE by beta plus 1, we can relate R pi and RE by beta plus 1. So little RE times beta plus 1 is just R pi. So you can go back and forth between those as well. In fact, when I did this, you never ever found transconductance when I learned all this stuff. You only found little RE and then went from there. But whatever way you end up doing this is fine. You'll find a way, one way or another. So, voltage gain, the other thing that we need to look at. And then on Wednesday, we'll look at kind of more specific examples of how to use this. If we look at the total collector emitter voltage, remember this is a combination of AC and DC because it's a little v and capital C, capital E. So we have VCC, which is the DC value of voltage, and then we take minus IC, which is a combination of AC and DC, times RC. So we can split out the two parts of the collector current. We have the DC part and the AC part. And then we can distribute the DC parts with the other DC parts and then have the AC parts by themselves. And we can combine VCC minus ICRC because that's the DC value of VCE. So what this means is that any signal at the output is going to have a DC offset of VCE. And then it's going to go up and down depending on what the collector current is, the AC collector current. So that's why VCE needs to be about half VCC, because it needs to be able to go up and it needs to be able to go down without either reaching VCC or saturation. So that's what we do. So the voltage VCE, just the AC part, is just minus ICRC, and then we can actually substitute in GM VBE RC for that. And then we can find the small signal voltage gain. Since it's defined as VCE over VBE, we just put the VCE on the top, put VBE on the bottom, cancel everything out. We get minus GM RC, which is almost exactly the same as MOSFETs, except we used RD instead of RC. So when we use it with a transconductance model, it looks a lot like a MOSFET. It won't always, depending on the configurations we use, we won't always end up with a transconductance term. Sometimes we will end up with ratios of resistors because we have alpha and beta that can relate these resistor values. So sometimes we end up with equations that don't include GM at all and don't look like MOSFETs, but this one does. This one looks a lot like a MOSFET. So the models we have, this looks very much like the hybrid pi model that we had for MOSFETs. We're taking VBE and we have the resistance R pi that VBE is across, and then we have a current source that magnifies that voltage into a bigger current and we get the values out. But we can also use the current controlled model, and that is just as common and just as valid. It gives you the exact same results at the end. So depending on what ends up being the easiest model to use when we analyze circuits, we'll use one or we'll use the other, and either one will work, and you get this, like I said, you get the same answer both ways. We can add in R out, since the early effect is what determines the value of R out. Remember, the slope of the lines is GM, and we can determine R out from GM. So when we do that and we add R out, then it's just in parallel with RC as long as the emitter is grounded. If it's not grounded, then it's a completely different problem, but we're not going to worry about that so much. We can get R out just by taking the early voltage and dividing by RC. Again, that's almost exactly the same as with MOSFETs. And we can also put that into a beta IB model and do it that way. Yes?
How would you find VA in this situation?
You have to be told what it is. Yeah, you do have to either extrapolate it yourself or be told. So yeah. We have T models for BJTs as well. Remember, we had those for MOSFETs. I'm not going to go tell you how we get from one to the other because it's exactly the same process that was done with a MOSFET. The only difference is with the T model for a BJT, we use alpha and IE instead of beta IB. That's just the way it's set up. But either one of those, again, will give you the same answer. So let's see. So we're going to go through an example that kind of goes through the process of doing the DC and the AC part. And first of all, we have a typical, we almost call this a conceptual amplifier because we would never actually set it up this way with 2 voltage sources and all that. But this is just so we don't have to go through a lot of the DC stuff, just a little bit. So we have a circuit in which we have a VN, we have a VBB and a VCC that set up the biasing, and we want to find the voltage gain. The first thing with any of these circuits that you have to do is the DC analysis first. So in the DC analysis, we turn off the AC source, so that goes away, and we pretend this is just a DC circuit. When I cover like overall discrete amplifiers, there's oftentimes capacitors that connect. In fact, I think for the lab, there's an AC source connected with a capacitor to the DC, and the capacitor just isolates the AC from the DC. So it makes it so that when the AC is on, the capacitors all look like shorts. When the DC is on, it looks like an open circuit. So we can take it out and it doesn't affect all. So we can find IB by just taking VBB minus VE. Again, don't ever try to memorize all these equations. It'll be different every time. So you just have to basically look at the circuit and know that you have 0.7 volts in the PN junction that's forward biased, and we have VBB of 3, and we divide by RB, and we get 23 microamps for the current IB. Then we can use beta to find IC, and then we can find the collector voltage, which we may need, we may not need, but we'll find it anyway because that's part of the Q point. Basically, the Q point is IC and VCE. So we'll find that, and we can determine the transistor's in active mode because the collector voltage is 3.1 volts, which puts that junction reverse bias, the other one's forward bias, so we know it's in active mode. We don't have to do some weird calculation. It wouldn't work as an amplifier if it wasn't in active mode anyway. So if it was in saturation, we'd kind of be done and say, okay, this amplifier won't work because nothing will come out. So once you get those values, really IC is the one that you can use, or IE if you want, either one. To get little RE, we need to have IE, but we already have IB and IC, so we can just add them together. So we get the hybrid pi parameters. We can get little RE as VT over IE, and I just added together IB and IC to get that value. And then GM we can find as IC over VT. And I will say that frequently the value of GM is considered to be like approximately 1 over little RE, and little RE is considered to be approximately 1 over GM. And that's because IC and IE are often really, really close together. So sometimes it's assumed that 1 over GM is little RE. That's just one of the assumptions that's made because IC and IE are going to differ by so little. But usually I use the actual correct values, unless it's inconvenient, then I don't. Anyway, we can find our pi. We can either take beta over GM and find it, or we can take beta plus 1 times little RE and find it that way. Both ways we're actually using a given parameter and a derived parameter. But that's one way to check and see if you got the right answer, because there's two different ways to do it, and you should get the same answer both ways. So now that we have the parameters to go into the AC part, we basically go back to the original circuit and turn on the AC and turn the DC off, which means that all of the DC sources look like shorts. The value of VBB goes away, and then VCC turns into a ground because it's shorted. So that point up at the top of RC becomes a ground. And then we just go and put values into the model. And I think I used the transconductance model for this one. And all we do is put the values in where they're supposed to. RB is going between it's going between VN and the base, so that's where we put it. And RC is going between the collector and ground, right there. It's between the collector and ground. So we put that in parallel, we get the model, and then we just determine what the values are. We take the values that were determined from the analysis and just put them in. So we put in the R-pi value, the GM value, we go and put those in, we put in the resistor values, and then we have a complete model circuit, and we just want to figure out what the gain is. We can analyze it. VBE is going to be the voltage division between the 100K and the 1.09K. So we're actually going to lose quite a bit of voltage there because 100K is a whole lot bigger than 1.09K. So we're going to lose a good bit of VN to start with, and we're actually going to end up with about 1/100th of VN actually at the base emitter. So kind of a small value there. Most signal resistances aren't as big as 100K, so that helps a little bit. Then we can figure out V out. Remember, V out is just minus GM VBE times whatever the output resistance is, which I think I left. Let's see. I think I may have left a number off of there now that I look at that. Or did I? I did. I left a value off of there. And I'm trying to figure out how I did that. I think I came out with the right number, but I left the number off. Because I have GM, and then I have VBE, but I don't have RC, which I need there somewhere. But if you do 0.092 times 0.01, I think you still have to multiply it by 3K to get minus 3.04. If someone can check that for me, I think that's correct. So we should have 3K ohms right in there somewhere. Otherwise, I don't see how we would get to 3 otherwise without multiplying everything by 1,000, 3,000. Does that come out right?
I'm just getting 0.92.
If you take 0.092 times 0.01 times 3,000.
Oh, 3,000.
Yeah, that's what.
2.76. Okay.
Okay.
I'm sorry. 2.76.
You got 2.76?
Yeah.
Okay.
I don't know why I couldn't do the 1,000.
I don't know why it
Negative
can.
2.76.
Okay, yeah. I'll go through and fix that later. But anyway, so that means that this would be negative 2.76. I don't know where 3.04 came from, but I think that's from what's his name's original notes. So I got to go check that. Anytime I don't pull out my calculator, that's the one time when it doesn't, work. All the other times I'll calculate it out like, yep, that's right. And then I'll get towards the end, which is where I am now, on like the last slide. I'm like, oh, yeah, whatever. Okay, let's go on. So that's how I end up in trouble. Yes?
Are you going to update the slides?
Oh, I always do, yeah. When a minute I go to my office, I change it, And then I also update what's on D2L, because I know next semester, all this stuff will get migrated over, and if I don't fix it immediately, when I was a younger teacher, I used to forget. I would do presentations and then I would forget to change it. And I would literally have the same mistake that went on semester after semester. And I finally got to the point where it's like, I've been looking at the same typo for like 6 semesters. I need to fix this. And then I would forget again. So yes, I'm going to fix that immediately. There are times when the morning before class, I'll look at something and go, oh, that's not right. And I'll change it. I'll change the slide right before class, which I already did with one thing. So anyway, last lecture on Wednesday. It's very similar. If you need to look through the slides to do the homework, it probably would give you enough information to do that, but I'll cover it officially then.